As we saw in the previous video, light diffracts in the real world, and maybe not visible for us in everyday life, but this is what happens. And last time we ended with this picture where we had this waves produced in a pond. What we'll see is that light does have the same property. So here's another picture. This is a bunch of boats actually traveling together, and they're all producing waves. And what's going to happen is, if we think about what happens in the water, when two waves come across each other, say from this boat and this boat, we can see that the area that they cover will start to get these really large peaks in the middle and some really deep valleys, depending on if the waves are both hitting exactly the same time. You can see actually a little bit better in this upper picture. You'll start to see this little checkerboard pattern. And this is something that happens in the ocean or in any smooth water. And also, we're going to see it happens in light. So what happens is we got to make sure that we produce the waves in a way where they'll interact. So there's this experiment called Young's double slit experiment. And really what happens is Young took a light, shined it onto a piece of cardboard or something equivalent that had two small little slits. So it produced two wave sources with the same exact properties. What happened is he saw that this pattern over on the right had a series of bright bands and dark bands. And the sources, it starts from a source, goes through 2 points. The bright bands we call constructive interference because the waves are arriving at exactly the same time. And the dark bands are called destructive interference. And this is what happens when one wave arrives with its peak while the other wave arrives with the valley. And we'll see that when this always happens, we get these points of destructive interference. And if you don't believe me in that animation, this is actually a real picture of what's happening. Again, we have our two light sources, and we'll see over here we get bright spot followed by dark, bright, dark, bright. So what we want to be able to do is predict where these things are going to show up and see a little bit more why this is actually happening. So let's go ahead and look at what's happening in the double slit interference experiment. Light comes through, and as I said, light is a wave, so it has a wave property, has a wavelength. And if we look at the distance from the screen, from the source, our two little spots here, we'll see that this thing will complete a certain number of wavelengths. And if we happen to be right in the middle of the 2 points, we'll see that the distance from here to here and the distance from here to here, L1 and L2, are actually equal to each other. Just basic geometry. Now if we move off to another section in here, the way that I have this drawn in here, you'll see that we both start going down, then up, down, up. This is one starts going down, back up. And when they get to the top up here, you see that they're both exactly in phase of each other. They're coming in slightly different directions, but both of them are up at the same point, down at the same point. What we'll see is that L1 and L2 prime, L1 in this case hasn't changed, that we've actually added one extra down then up, one full wavelength. So if we start doing a little bit of geometry, we're going to define an angle, and this angle up here, so how far we are between these 2 points, we can approximate that to be theta as well, as long as the angles are relatively small. We'll see that L1 plus delta is equal to L2 prime. So the number of wavelengths we go through is the same. And from geometry, we can see that delta is equal to d times sine of theta, where d is our distance between our two sources. Again, delta is a small little extra wavelength. So we know that this extra wavelength in here is equal to delta. And if we actually generalize this, we can imagine that this will happen again at another spot up here. And what we'll see is that by combining these equations, we get a wonderful equation that looks like m theta, so some integer times the wavelength, is equal to d sine theta bright, where m is equal to 0, plus or minus 1, plus or minus 2. So this will tell us when does the waves both hit at the same point with the same spot in their sinusoidal curve. So when do they both reach the same maximum at the same point? So if we look back at this picture that we saw at the beginning, we saw that there's points where we get the bright lines. And if we look at m equals 0, which we define m equals 0, which is normally straight down the center, we'll see that if we substitute things in, sine of theta 0 is equal to 0 times the wavelength divided by d. And that's just 0 degrees. However, if we actually look at m equal 1, when we start substituting in, we'll see that sine of theta 1, so this angle, between that angle right there, is the sine of that angle is equal to the wavelength divided by d. And if we keep going, we can see this second one, m equal 2, this angle right here is proportional to, the sine of that angle is proportional to 2 times the wavelength divided by d. And we can figure out where our minimums and our maximums appear. Corresponding to that, we have what's called destructive interference. And you'll notice that we're going to change this equation just slightly a little bit. Instead of having d sine theta equals m lambda, it's going to be m plus 1/2. So we're going to introduce a half wavelength. So that just means when one is going up, the other one is going exactly opposite of it. And it'll always interfere, but they'll interfere destructively, or they'll cancel out. So again, we can use m to index, so we notice again this 1/2. Our counting is a little bit different in here. I'm going to set m equals 0 at this point. We could have easily chosen the bottom one, but just for good measure, m equals 0 falls at 1/2 length lambda of the wavelength divided by d, and that'll be the sine of the first dark band or dark fringe. Same thing with m equal 1, we're going to get minus 1/2. So we start to see, as we include more of these 3/2 or -3/2, that we're always on the half integer steps of wavelengths. And that's really what the key point is that we need to destructively interfere, one wavelength has to be, or one length has to be a half wavelength or 3/2, 5/2, one of these half wavelength integer increments from the other.